What kind of amateur production is this?
You're running the show, you tell me.
I'm not running the show. This is Katie who was supposed to take care of this before we got here. So. I just didn't tell her that. All right, we're going to talk about magnetos. And I'm sure there's some joke in there about magnetos or neatos. I don't know.
That was hilarious, Kevin.
I couldn't put it together, man. Puts the neato and magneto. I don't know. I don't know.
You should do stand up.
Nope.
You're standing up.
I am standing up. All right, we're gonna go black again. All right, so here we go. So, all right, so half of you are kind of off the hook, and the other half of you are on the hook, because if you're first semester, you're like magneto. I kind of get it. And if you're second semester, you better now be a genius on them, right? No. Tim's gonna spit his coffee out at me. You're looking at me.
It's not my fault.
That you broke.
Well, let's talk about magnets first, because we got to understand magnets from where we're going from here on out. So, what is a magnet? A magnet. A thing that sticks to things. Well, that's about what I'm going to write. Magnet. An object that attracts ferrous metals. What is a ferrous metal? Well, guy there in the back, his name's? Ferrous. Ferrous, tell us about it.
That's Bueller.
It's like the name your parents named you Steel. He's the man of steel is Ferrous. It's kind of cool. All right. You could say it's something that produces a magnetic field. Magnetic field external to itself. External to itself that reacts with magnetic substances. All right, so magnets. Well, I got to get some magnets here. So just for fun, I've got my two little tiny magnets right here. And just take those apart for me real quick. Real quick. Tim, could you take those apart? They're just magnets, buddy. Just pull them apart there. Did you not eat today?
He's just a fuel guy. Leave him alone.
You just get them apart for me? No? You kind of don't want to get your fingers stuck in
Put them on your
it.
earlobe.
Huh?
Put them on your earlobe.
On my halo? No. Thanks.
Put on MJ's earlobe.
Huh?
MJ's
Make it
earlobe.
fit.
Yeah. Yeah, you can play with it. Yeah. Anyway, so magnets can actually be pretty stinking strong, or Tim's just really not strong. I'm not sure.
Probably both.
I don't want to pick on him. Just tired. Maybe he's like a superhero, and magnetic lines of flux are like kryptonite to him. Have we ever thought? Has that occurred to anybody? All right, magnetic field. What is a magnetic field? It is invisible. Invisible lines of force, or sometimes called lines of flux, that leave the North Pole, that's where Santa is.
Really?
Liar.
And enter the South Pole.
Who lives there?
Now, I don't know if anybody really knows that for a fact. I think it's just like, what is
Is this classical or is this electronic flow?
Yeah, and according to some stuff that I've read on the interwebs, that it is actually switched, and they anticipate it will switch again. So north becomes south, south becomes north. How would that possibly happen? You should know by now. What? This little rat goes down to the thing and he rotates the thing, and that's how it happens. Yeah. All right. Actually, I didn't realize I wrote this. This is purely theoretical, not actually known if there is any movement, but that's fine. So, magnetic flux is strongest near the poles. Near the poles. In fact, if I were to draw a magnet, north here, south here, like blue for this, they're the strongest here. And of course, it's going to go around, be symmetrical. They do not intersect, the lines don't intersect, and they don't cross each other. And the lines of flux actually tend to want to repel each other. So they start moving away from each other. So you'll never see one crossing another. They're going to look just like that. So they're strongest up here near the poles. I'll write this. Flux lines do not intersect. Flux lines do not intersect. And flux lines take the path of least resistance. So flux lines given an easier route to follow, they're gonna flow through that. Incidentally, so if we assume that flux lines go from north to south, what happens when they get to the South Pole? I turn around and go back to north. And if I were to drop this magnet and break it in half, this becomes the south and this becomes the north there. So how do you make two magnets out of one? I don't know. And when you think about this, also remember when thinking about flux lines take the path of least resistance, which has more resistance, air or steel? Steel. Okay, so air has more resistance than steel. All right, so we have a couple of different type of magnets, which you've pretty much been exposed to already. We have a permanent magnet. And a permanent magnet is the one that maintains most of its magnetism without the application of a force. So once you magnetize it, it stays that way. Now it's not going to stay that way forever, but it maintains most of it. So maintains almost constant magnetism without the application of a magnetizing force. What is a magnetizing force?
Rotation.
Electricity is kind of what I was thinking, but how are we going to do it with rotation? You're not wrong. I don't think. How would we get magnet? How would we create a magnet by rotation?
With an iron core, if you're spinning fast enough. If your airplane engine seizes up, you just take the magneto and spin it really fast.
Okay, I'm going to go with what I was thinking, since that's what I know. So put current through it. So that's what the big magnaflux machine is that we're going to be working with here pretty soon. And that's the thing I used to demagnetize your stuff. I just did the opposite. I ran a current through it, but I ran a current that was diminishing. So, but if I put a current through that's not diminishing or reversing polarity, well, to some extent I can reverse polarity, but put a strong enough current through iron, some sort of ferrous material, then I can align, we talked about this before, align the domains inside. Talked about that in this class. Where did we talk about domains? At some point, didn't we?
No.
What lecture would that have been on? Something. But anyway, so we can magnetize it. We align the domains and then we magnetize it. I know, now Justin's going to look it up. He's going to say, yep, we did talk about it, see? All right, so we have a permanent magnet. We have natural magnet. What's a natural magnet?
It comes from the earth.
There we go, it comes from the earth.
Okay.
The original magnets, a magnet found in nature.
Wild magnet.
Wild magnet. Well, you have little magnet reserves now where they're allowed to run. So, what is that natural magnet called? Come on. Huh? Is it gold?
No, I said like a rock, because
Yeah. Well, it's not called a rock. You're very close. Nobody knows? Huh? A lodestone. The lodestone.
I was thinking that, but I didn't know if I was right or not.
No, I know. I could tell by the look on your face. So lodestone. Actually, that name comes from, I'll put it, or leading stone. And that's what they came from, because explorers used it as a compass. So you take some lodestone, you put it in a little cup of whiskey, and on a string, actually. All right, give me another type of magnet. Come on.
Electromagnet.
Thank you. Electromagnet. And how do I make it? What is an electromagnet?
Electricity.
Coil. There we go. A magnet made by passing a current through a coil. So that item that I use to demagnetize your stuff for your rotor and impulse couplings, I put it inside of a coil. So inside of that coil were a bunch of wires running around in there. And so I just passed a current through it, but I passed a diminishing current, which demagnetized it. Now I could have gave it a magnetizing shot, which would have been a blast of current through there, and it would have transferred the magnetism. We got to do this. Left hand rule. Left hand rule. Well, there's a point to it. Left hand rule. I told you I won't make you memorize the rules because they can get confusing. So left hand rule. When a coil is held in the left hand, let's see, with the fingers point in the direction of current flow. I'll put when, oops, that goes there, left hand, when fingers point in direction of current flow, thumb will point to north.
Is that top or bottom?
Is north top or bottom?
No, if you're holding it in your hand.
This way.
Okay.
So your fingers point in the direction of current flow. So current comes in and it's rotating around in electron theory flow. Because I think about that, they had to change everything from right to left, didn't they? And they figured this out. So someone's, we gotta change all the rule of thumb. So current flow going around this way, that's the north end. Which is to say, if you then turn the coil around and put current going the other way, north and south are going to swap. the strength, this is important, of the magnet, the electromagnet, is directly proportional to the amount of current. Which is to say, the more current you put through the coil, the stronger the magnet's going to be. So to demagnetize your rotors and stuff, I was using, I believe, around 10,000 amps.
Whoa. That's it.
That's all I had. But it was very quick. I'm sorry, that's messing me up there. All right. Now, I want to make something that is very complicated not complicated. So I'm going to tell you about the two ends of the magnet. Two ends of the magnet. And I'm going to tell you it like this. First, I'll make it complicated. Then you go, what? All right, so we have the Earth. That's the Earth. This is where Tim is. Tim is right about there. All right, and so within the Earth, we have, in theory, a bar magnet. And we could say, in theory, that's the north and south end. Well, if that's the north and south end, and then I have a compass, it's not what I wanted my compass to look like. A compass, and this compass is pointing towards the north. Well, is this part right here a south part of the magnet, or is it the north part of the magnet? So it's a south bar of the magnet, right? Because opposites attract. So what I'm saying is, does this magnet look like this, north-south, or does it look like this, south-north?
Looks like this.
Oh, south.
Top one or the bottom one?
Top one.
Top one. Okay, well then the north end of the magnet's really the south end of the magnet. So if I say, hey, is that the north or the south? Well, it's the south. How do you know it's the south? Because it points towards the north? Okay, that can be very confusing for some people. Or maybe the bar inside of the magnet really looks like south and this really looks like north. That way the north end of the magnet points to this, points up.
Mine.
And if you don't get it, maybe you didn't get it. Yeah.
Is there ever a point, like if you're up in the North Pole, where you have a compass and it's pointing north, and then you walk past it?
There is. It's weird. It's you're walking, and suddenly it just goes like that. You turn around, you walk a little bit, and it goes, I don't know. Do I look like a polar bear with a compass?
You always are full of fun facts. I figured that might be it.
Okay, so in reality, first of all, the pole really isn't on the north. It's kind of offset a little bit, and then there are octagonal lines with errors and stuff. So it becomes a lot more complicated than I want to get into.
And then you go to Bermuda.
What?
If you're over the direct North Pole, it would just go crazy because it's a lot bigger than the scale at which you're walking.
Yeah, it comes out about the size of a pencil. Now I know it's an area. It's more okay. So to make this whole thing not complicated, and we can all understand and speak the same thing, I like to use these terms. The north seeking will be this end that points to north. Can you get on board with that one? That is just too simple.
Kind of sounds like I'm gonna have to.
You don't have to. You can make up your own thing. See how it works for you. So if I said, what side of the magnet is that? It's the south-seeking side. It's the north-seeking side. Well, there's no argument there. Well, it's not the north-seeking side. Yeah, it seeks north, doesn't it? So north-seeking points to south. Yes, Tim.
You say it's seeking. Does that mean like?
It goes to.
Looking for
Okay,
it.
so like if you're looking at it on the compass.
Okay, so
where
right
do you
here,
wanna go to?
this compass right here, this piece right here,
Yeah.
it's pointing towards north, right?
Yes.
So that is the north-seeking.
Okay.
North-seeking. So now you don't have to say, well, is it the south bar of the magnet going to the north inside the Earth, or is it the north side of a magnet going to the south bar of an Earth because this is upside down. It's two different theories. Doesn't matter. Say it's north seeking. Well, is it north or south? It's the north seeking. Don't be,
Hey Kevin,
Yeah.
is there a magnet in that home?
Magnetometer, an accelerometer too, right? And
And a barometer.
Okay.
and a thermometer,
And a thumb scanner.
which makes me think of my favorite joke.
Did you need it just for that, Kevin?
Huh? I did. Because Katie listens to these home, and my wife says, "Would you stop telling that joke? It's stupid." So, sorry, honey.
Wait, she didn't hear the joke you gotta tell her.
No, she'll know. She's
she'll
like,
know.
she knows.
Watch the video.
All right. Okay, I'm not gonna write it, but I said it. The Earth's magnet is also not aligned with true north. So anyway, all right. So theory. What do I want to talk about? Theory. I want to do this. Believe that. Oh yeah, this is my.
How'd you get H?
Don't
worry about it. Just deal with it.
All right, I'll do G, just because you guys are just a tough crowd. See, this is why I don't do. That's why I don't do stand up. I have 30 some hecklers right here I can deal with.
At least we're nice to you.
That's really all you're putting for G, Kevin? Just Earth?
That's it. You don't get to know.
Earth.
Earth.
Narrated by
Just Earth?
Gary.
That's all
You are here. Some of you make sure some of you write that down. It's kind of what I already said. The Earth has a magnetic field like a bar magnet. Since opposites attract and like repel, the Earth's magnet is, well, this is one theory, actually upside down. South is at the north, the north is at the south. That's one theory. The Earth's magnet is also not aligned with true north. But I don't know. I don't think we need to get into that because it's not really.
So why'd you put it up there?
Because otherwise I'd be off on the little line right here, right? So, I know. You know, classes that I like, I tell them a little bit more.
That's so sad.
You just want to let us know we're here?
I try and keep it at a level that you guys can understand. There's certain things I don't know that all of you know that. So you are here,
Where's here?
Earth.
Oh. That's scary.
All right, theory. It's believed that atoms have a magnetic field when electrons orbit randomly. Justin, where did we already discuss this?
Oh Lord, I have no idea.
You didn't look it up?
I did, but you write so fast that I had to catch up.
Oh, okay.
He had to get on there that he was here. So he had to stop looking at it.
No, that was
All right, so where does this magnetism come from? Well, one theory is that atoms have a magnetic field, and when the electrons orbit randomly, there is no magnetic field. But if you can get them all to line up and do the same thing, that they exhibit a magnetism inside of a part. So that's what's going on here, perhaps. All the atoms are lined up to the point where poor Tim can't even pull these tiny little magnets apart.
Let's see if I can do it again.
You're going to hurt yourself is what's going to happen.
No, I want to see if I
That's a
can do it.
lot. No, he signed a waiver. Go for it.
Yeah, it's like
I'll give them to you apart.
Okay.
Put them together. All right, so let me see.
Someone did not put their weed.
All right, I'm just putting it is believed.
Mr. Prism. He's been working out.
Believed that atoms have a magnetic field.
Come on, can someone do it?
Go, Butterfingers. Did you just have popcorn?
When electrons
You stealing his magnets?
I got it right down.
orbit randomly, the fields cancel each other out. But when the part is exposed to a magnetizing force, the atoms or the electrons the electrons align, and the part becomes magnetized. And another theory that I like is the domain theory. This is a theory I first learned, is that the part contains little magnets that are aligned when the part is magnetized. And what that is saying is if you take a part and then within it you have all these little bar magnets that are just going to be randomly going in different directions with their little north and south, north, south. And so this part right here is just not magnetized. So everything's just going kind of every which way. But when you apply a magnetizing force to it, run current through it, all of the little domains are going to want to line up inside there so that we get a north, south, north, south, north, south. So this becomes north and this becomes south. And they all line up and the part is now magnetized. And to get it unmagnetized, demagnetize it, all you have to do is scramble them. And you can do that with diminishing current or AC field. And that is something we're going to talk quite a bit about next semester. Again, actually next 8 weeks when I come back, when we do non-destructive testing. So, but we're going to talk about it now too. So you get a double shot. Residual. Residual magnetism. That's a magnetism left in a part after the magnetizing force is removed. So if I put something in and I magnetize it, like, okay, you guys are magnetizing your rotors inside that little machine. Well, if you were to actually measure the magnetism that that part contains while you're pushing the button, it's going to be significantly higher than when you take it out. So what's left is the residual magnetism. Is the magnetism. Justin, can I just do cursive? Would that be a problem for you? I can go much faster.
Write better.
Well, you can write yours in cursive. Is the magnetism left in a part? Yeah. Just give me a minute. You can go on break. You don't have to Is the magnetism left in a part after the magnetizing force is removed? All right, that sounds like a good place to stop so that Dennis doesn't ruin the rug.